Imagine a world where wheat farmers battle invisible foes that could wipe out their harvests, putting global food security at grave risk. Now, picture a groundbreaking innovation in Mexico that's turning the tide faster than ever before. But here's where it gets exciting. What if breeders could skip years of waiting and predict plant success right from their DNA? Dive in to discover how this is reshaping agriculture. In the heart of Mexico, a pioneering project has reached its triumphant conclusion, focusing on crafting elite parental wheat lines that boast heightened defenses against various diseases. These lines serve as versatile building blocks in breeding initiatives, akin to pre-mixed ingredients that streamline the creation of a grand culinary masterpiece, allowing breeders to swiftly incorporate desired characteristics. Entitled Deep Scoping Rapid Cycle Recurrent Genomic Selection to Accelerate the Breeding Pipeline for Quantitative Disease Resistance in Wheat, the initiative tackled two formidable fungal adversaries, Septoria tritici blotch, STB, and spot blotch, SB. With their prevalence on the rise due to shifting climate patterns, these diseases pose a dire threat to wheat yields and the sustenance of communities in Southeast Asia and Africa. For beginners in plant science, think of these as sneaky pathogens that infect leaves, much like how rust corrodes metal over time, but in this case they erode the plant's ability to produce food. Crafting resistance against such foes is no simple feat, as it hinges on the synergistic action of numerous genes, a phenomenon known as quantitative resistance. This complexity, as detailed in a study, https://access, online library, wiley.com/doi/1002/T20531, makes traditional breeding techniques, which often rely on trial and error in fields, a slow and arduous process. And this is the part most people miss. Without advanced methods, breeders might spend decades perfecting traits that nature has woven intricately into the plant's genetic fabric. Conventionally, breeders endure multiple years evaluating how plants fare in real-world field conditions before choosing the best candidates for the next round of reproduction. But this project unleashed a smarter, data-centric strategy, leveraging DNA information to forecast performance and expedite selections through genomic selection, a bit like using a crystal ball powered by genetics instead of waiting for rain to see if the crop thrives. This shift dramatically compresses breeding timelines. Breeders can now churn out several generations in the same window, delivering disease-resilient wheat strains to growers at record speed and bolstering long-term food security. For the specific diseases in focus, the outcomes mark a revolutionary leap in protective capabilities. The CIMMYT experimental station in Toluca, Mexico, offers perfect environmental settings for pinpointing wheat varieties with strong foliage disease resistance. Credit: CIMMYT/Alfonso Cortez. So, why should this capture your attention? The project stands as a robust proof of concept, with findings that can be applied broadly to other wheat breeding endeavors. Here's what that translates to in practical terms. Breeders can now reuse parent plants after just 3 years, a sharp reduction from the previous 5 to 7 years. Beneficial genetic traits build up more rapidly, propelling overall genetic advancement. Shorter breeding cycles mean enhanced varieties reach farmers sooner, potentially averting crises in vulnerable regions. This fresh approach we pioneered in the project is truly catching on among breeders. I believe we've sparked a genuine shift in perspectives. For me, that's the pinnacle achievement, shares Susanne Dreisigacker, wheat molecular geneticist and project lead at CIMMYT. The old-school mentality held that early parent selection in breeding was impossible without solid field-based phenotyping, measuring traits like disease resistance in real environments. What we accomplished here is selecting the top performers purely from their genotypes, then reusing them. Even in standard breeding programs now, experts are adopting genotype-based recycling far earlier. And that's a mindset revolution, realizing you don't always need 2, 3, or 4 years of field trials to deem a line parent-worthy. A paradigm shift in thinking. Dreisigacker's team is riding the wave of this success into fresh ventures, customizing efforts for regional threats. In South Asia, the spotlight is on spot blotch, while South Africa zeroes in on septoria. I anticipate that as these parental lines integrate into widespread breeding, we'll yield superior products. It's comparable to whipping up a cake with a pre-made base. You skip fretting over the basics and concentrate on the finishing touches, she illustrates. Colleagues' reactions have been overwhelmingly positive. The feedback is now, absolutely, we must apply this to other diseases too. Backing arrives from multiple fronts. Our pathology experts, who handle disease testing, are all in because they witness tangible gains. This signifies a profound transformation in outlook. Initially, the idea faced skepticism. Now it's a whole new ballgame, with heightened recognition of its feasibility and burgeoning enthusiasm for replication. Susanne Dreisigacker unveiling project results during a field tour in Toluca, August 2025. Credits CIMMYT. But here's where it gets controversial. Is this rapid tech-driven approach overshadowing the irreplaceable value of hands-on field experience? Some might argue that rushing ahead with DNA predictions could miss nuanced environmental factors, potentially leading to varieties that falter in unpredictable real-world conditions. What if we're trading tradition for speed at the risk of unforeseen failures? Gyre is spearheading the worldwide rollout of this methodology, drawing keen interest from universities and cutting-edge research institutions. Workshops have disseminated the technique, enriching expertise across Gyre-affiliated breeding networks. Peering into the future, sustained financial support is vital to sustain the upgrade of local partners' breeding capabilities, bolster underfunded national programs for access to sophisticated genetic tools, broaden the techniques used to more crops, and confront multifaceted climate hurdles demanding the amalgamation of various resilient traits. About Crops to End Hunger. Launched in 2018 as a funder-driven initiative, Crops to End Hunger (CIMMYT) is now in its Phase 3, backed by GIZ, and dedicated to revamping breeding programs and networks in collaboration with National Agricultural Research and Extension Systems, NARES. Investments have poured into station upgrades, training personnel on state-of-the-art tools and methods, and forging essential resources to speed up crop improvement. By enhancing breeding efficiency, CIMMYT ensures that better, more productive varieties are created and distributed to small-scale farmers with greater haste. Resources. Grab the program brochure here. https://drive, google.com/files/d/1x7q4nbw93zf3s2view x12rtvr1/view?USP sharing. Dive into the research paper. Siddhant Chaudhary, Mukesh Dubey, Dan Funk Jensen, Laura Grenville Briggs, Akash Chawade, Magnus Carlson. Plant genotype-specific modulation of clonostocies rosea-mediated biocontrol of septoria tritici blotch disease in wheat, BMC Plant Biology, https://bmcplantbiol, biomedcentral.com/articles/10.1186/s12870-025-06620-9, 25, 1, 2025. Note: the original had a different link, but preserving context, this seems to be a related or updated reference. Catch up on the news story. From Gene to Impact, Science and Partnerships to Transform Agriculture. https://www.org/news/from-gene-to-impact-science-to-partnerships-to-transform-agriculture. Main image. Visible damage from septoria tritici blotch on wheat leaves in Toluca, Mexico. Credit. CIMMYT/Alfonso Cortez. What do you think? Could this genomic revolution in wheat breeding spark a new era of food security? Or are we risking over-reliance on technology at the expense of traditional wisdom? Do you agree that shortening breeding cycles is worth any potential trade-offs? Or should we prioritize thorough field testing? Share your views in the comments. We'd love to hear differing perspectives.